Hello everyone, welcome back to this playlist of metric spaces. So far in this playlist, we have covered the definition of metric space. Then we were doing some examples of metric spaces in which we have already done usual metric on R, and using this usual metric, we have defined some other metric on R. So now let us move from R to some other set, that is Rn. Before directly defining a function, let me first recall what a set Rn looks like. So, till 12th class, you must have done the set of R2. How does an element of R2 looks like? It is an ordered pair like A comma B. So if I want to define the set R2, if I want to give the definition of R2, how will I give it? I will say that R2 is the collection of all ordered two tuples. Why ordered? Because order is important here. Here 1 comma 3 and 3 comma 1 are two different elements. So we cannot change the order. If we change the order, the element will change. So it is collection of ordered two tuples. This is the definition of R2. And similarly, and every element or each coordinate here belongs to the set of real numbers. A and B are both in real numbers. Similarly, we know how R3 looks like. It is the collection of all ordered three tuples. Here we have three coordinates and we are representing it as A comma B comma C. You know how an element in R3 look like. Here we had X coordinate, Y coordinate and Z coordinate. So any element here is represented as X, Y and Z. So we have three coordinates. Distance in x-axis, distance in y-axis and distance in z-axis. So this is how the elements of R3 look like. So R3 is a collection of all ordered three tuples. Again, order is important. So similarly, we can define, okay, so R3, the element A comma B comma C, where A, B and C all three are in the set of real numbers. Can I write it as A comma B comma C as A1, A2 and A3? This is just a notation. This was a notation, this was a notation, and even this is a notation. Here we have given an index. The element in first coordinate, we have given the index 1. Element in second coordinate, we have given the index 2. Element in third coordinate, we have given the index 3. So just in order to give the identity to an element to which coordinate it belongs to. So R3 is a collection of all ordered three tuples, say A1, A2, A3, where A1, A2 and A3, all these three numbers are from real set. So R2 was the collection of all ordered two tuples. Similarly, R3 was a collection of all ordered three tuples. That means R2 has two coordinates, R3 has three coordinates. Similarly, Rn is the collection of all ordered n tuples. We have n coordinates here. An element in every coordinate is a real number. So Rn is a collection of all element of the type A1, A2 up to An, where each of the Ai belong to R. Now we have seen what a set Rn look like. Now to prove that Rn is a metric space, we will need a function from Rn cross Rn to R, right? So before defining the function, let me first recall something. Do you know in R2 how we used to define distance between any two elements? Say we have 2 points in R2, A and B. What was the formula for the distance from A to B? Yes, I am talking about that distance formula, which was distance between the 2 points A and B is under root of difference between the first coordinates of A and B. Here the first coordinate is A1 and here is the first coordinate B1. So difference between A1 and B1 square plus distance between the second coordinate A2 and B2 whole square under root. This was the distance formula in R2, and similar distance formula we did to find the distance between any two points in R3. So similarly in R3, if we have 2 points A1, A2, A3, this is the first point, and B1, B2, B3 as the second point. How we will find the distance between these 2 points? Again the same formula, but here we have 3 coordinate. Here we had two coordinate A1 and A2, and here we have 3 coordinate A1, A2, A3. So the distance formula will be under root of difference between the first coordinates of A and B square plus distance between the second coordinate of A and B square plus distance between the third coordinate of A and B square. So A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square, and keeping all of them under root. So if I have one more coordinate, say if I am finding the distance between 2 points in R4, there will be only one increase, that is plus A4 minus B4 square. So now I think you can guess what can be a formula for R. So you know distance between any 2 point in R3 can be written as this. Can I write it in reduced form as summation of ai minus bi square, where I varying from 1 to 3. For under root I use the power half. Can I write it as this? If I expand it, it will give me the same thing, right? Under root, for I is equal to 1, it will be a1 minus b1 square, then sum, then a2 minus b2 square, then sum, then a3 minus b3 square, then sum, and whole root. It is up to 3, so at a3 we will stop. So I can write it in summation form as this. Okay, so why I am writing it as this, I want you to write it as this because it will help in case of Rn where we have n coordinates. So writing this formula again and again will take a lot of time, so just write it in reduced form. So if I talk in Rn, elements of Rn are n tuples. So distance between any 2 points, say first point is a1 a2 up to an, second point is b1 b2 up to bn in Rn. So what will be the distance between them? Summation of ai minus bi square, where I varying from 1 to n. The coordinates are going up to n. So I is varying from 1 to n, and for root I have used the power half. If I expand it, what will I get? That is square root of, for I is equal to 1, it is a1 minus b1 square. For I is equal to 2, I have a2 minus b2 square. For I is equal to n, similarly I have an minus bn square. Okay, so till this point I have discussed what a set Rn look likes and how do we find the distance between any 2 points on the set Rn. If we have any 2 point in Rn, how do we find the distance between those 2 points? Now do you remember on the set R we used to find the distance between any 2 point x and y as mod of x minus y, and while defining metric on R, the first metric we defined was the distance metric itself. we define the metric D from R cross R to R as D of x and y is absolute value of x minus y. That was the distance between the point x and y. Similarly here, now we know the set Rn and we know the formula to find the distance between any 2 points. So using that distance formula, we will define the metric on Rn. So how will we define the metric from Rn cross Rn? We will define a function from Rn cross Rn to R as d of x comma y is distance between the point x and y. So here also we are going to define the function, that is distance function, distance between x and y. So if we take x to be Rn and d from Rn cross Rn to R as d of xy, where x and y both are the elements of Rn, and you know how an element of Rn look like, it is ordered n tuple. So x looks like this, x1 x2 up to xn, and y looks like this. So if I define a distance between x and y, it is summation of xi minus yi square, where I is running from 1 to n under root, right? So this is what I defined the function. Now let us check if Rn with this function turns out to be metric or not.